Good evening, y'all. Welcome back to another Electronics Bash Fundamentals of Arduino stream on a Sunday night. Hi, I'm Jeff Glass. I know most of you out there, but maybe there's some of you I don't know out there. And if this is your first time tuning in on a Sunday evening to talk about Arduino and fundamentals of electronics and all kinds of fun stuff, then hi. I hope you'll shout yourself out in the chat and introduce yourself. Or if not introduce yourself, then I would be super curious where geographically people are coming in from tonight. As always, we got a little countdown time. I always get the point wrong. Countdown timer over here. We'll give folks who are straggling just a couple minutes to jump in before we get started. But I think we're gonna have a good night tonight. I was watching back through what we did last week, and we covered so much ground. I think probably a little too much ground. We talked about analog input, analog output, serial input, serial output, and we did tones and buzzers. And honestly, that was a little bit slammed. Like, took a little over 2 hours to do all of those things. And so this week I thought, I think at the end of last week I rambled off 3 or 4 things that we might touch this week. But in thinking about it, I think it will be more valuable and more interesting to simply look at a couple of specific things, and then we can dive in a little bit deeper with examples. We can be a little bit more responsive to questions and ideas that people come up with as we go, just because we won't feel so slammed in having to try and get through a bunch of different topics all in the same evening. I should say this evening is brought to me. It's not brought to you. It's at least brought to me by A Little Crazy, a Belgian-style pale ale from Revolution Brewing Company here in Chicago. They have several tap rooms and several breweries. And Revolution is actually where my wife and I got married, just about exactly 1 year ago. It'll be a year ago sometime next week. So we'll have ourselves a quiet little staying home anniversary this year, but I think we'll have a good time. So thanks to Revolution for taking good care of us last year and tonight. I'm in my mind, this is like a drink along stream. I don't know if other people are drinking things out there. Like, do you guys have beers or beverages, or are we just like water, hardcore, Gatorade, like powerhouse stream? I don't know. I'd be curious. Oh, very tasty. We've been trying to, of course, shop a little bit local, have a good, support our local businesses where we can. Microcontroller says, Two Brothers Prairie Path? Yeah, Two Brothers is also pretty local, very tasty. Kenneth drinking kombucha. PF Jenke drinking water. Yeah, there's no wrong answer. And this is no shame on people who don't or can't drink alcohol. Like, it's a vice of mine and I enjoy it, but this is not pressure. I just, whatever drink you have, I hope it's helping you relax on a Sunday night. For the next 90 minutes, I'm sure it'll just be 90 minutes. We've never gone over 90 minutes on this stream, ever, at all, never. We're just gonna relax and enjoy each other's company and talk about Arduinos. Yeah? So, shall we dive in? Let's do the thing. So, this week, let's get the slides going. This week, we're gonna talk about a bunch of different things. Only a couple of different physical, tangible Arduino things, which is, I think, what's going to provide that nice focus for us this week. Servo motors and stepper motors, in that order, are our two sort of outputs that we'll look at. We'll also look at... Oh, you know what? I should double check. Can you hear me? I hope you can. Did I turn it on? Yeah. Servo motors, stepper motors. We'll talk about while loops, or do while loops, which is a control structure that we haven't talked about yet. We'll talk about randomness, how to do things randomly, and how to do random things. And we'll dissect that a little bit later. And as part of our work with servo motors and stepper motors today, we're going to need to start involving code libraries for the first time. And so we'll talk a little bit, just a little bit, not about building them or making them, but what a code library is and how you can use them to give your code additional functionality, if that sort of makes sense. Audio is great. Thanks, PF Jenke. So before we dive into servo motors and stepper motors, I realized that as I was going through what might generously be called the lesson plan for today, that there is a bunch of times when I'm going to want to say a servo motor is like a DC motor but, or a stepper motor is like a DC motor but. And I realized we haven't actually talked about what a DC motor is. In my original conception of what tonight was, that would have been sort of the first thing that we talked about, but in any case, what I want to do is give you one slide, like just a taste of what a DC motor is in case anyone's not clear. We will probably get to powering DC motors next week as part of our talk on transistors. if that's cool. So just for like anyone who hasn't encountered them, for the purposes of today, here's all that we need to know about what a DC motor is. It's a little tiny device. It could be a large device, but a lot of times they're very small for our purposes. You apply a DC voltage and they rotate. For many of them, if you reverse the polarity of that DC voltage, they will reverse direction. I realize we haven't actually talked about DC and AC power and what it means for polarities to reverse, but for the purposes of this evening, we can think of a thing that we apply a little bit of power and the thing turns. How you would power that with an Arduino? Well, you'll recall from, I think from our first stream that we talked about the current limit on the output of any specific Arduino pin or any specific point of connection. And for most DC motors, we're not going to be able to supply enough power directly out of the Arduino to power a motor directly. So we would need to use something to boost the amount of either current or voltage or both available to us, and we would use a transistor for that. And that, I think, like I say, is going to be next week's topic. But for the time being, a DC motor, you give it power and it spins. I hope you'll go with me on that, because it's going to let me say things like a servo motor is like a DC motor with feedback built in. Right? Now, before we get too far ahead of ourselves, let me show you a little example of a DC motor over here. Let me zoom in a little bit. This is a little hobby-style DC motor. They come in all kinds of different form factors and all kinds of different sizes. This is just a pretty common one. If you've ever built a little like remote control car kit or a solar-powered car kit, you often see this kind of style. It's got an output shaft here. It's got 2 input terminals. You put voltage on it and the output shaft spins. Like a lot of the things we'll look at tonight, this one has you can sort of see a keyed shaft there where one side is cut off. So if you were to put a knob on it, and that would give you a place to affix your knob or your wheel, your propeller, or whatever you might be outputting with. So DC motor, apply voltage, and it spins. How to apply voltage next week. So a servo motor is like a DC motor, usually a DC motor, with feedback. And what does that mean? Well, servo motors come in all kinds of different sizes, right? But sometimes, if you experienced working with servo motors before, you might be thinking of these little tiny things. In fact, that's what we'll be working with tonight. But servo motor just means a motor with feedback, so they come in all kinds of different form factors, from the very small to the very large. These are some industrial ones, just an image I found on Google. In my current job as an exhibit tech for a science museum, we're currently in the process of repairing a giant exhibit installation called the Wave Tank, and I think did I see Brian over here tonight? I think Brian's here. Yeah, Brian's here. Brian is intimately familiar with the Wave Tank. Basically uses a servo motor to push a giant plunger into a tank of what's supposed to look like water, but is actually mineral oil, to create a wave that moves through the exhibit and demonstrates a natural phenomenon. And that servo motor is a strong. It's about that big, and it has feedback in it, so it always knows where it is. And that's the key takeaway: is that there's lots of different mechanisms, but in general, a servo motor is going to have some kind of feedback. And for our purposes, at least for the kind of hobby servos that we'll be playing with today, this is the mechanism of that feedback. And before we get into that diagram here, I'll show you what I mean. You might think about, let's say we wanted to have a motor that knew where it was and wasn't going to turn very far. Like, let's say we were going to have the steering mechanism on an RC car that really only needed to tilt the wheels, maybe 45 degrees in either direction. So we needed a thing that was going to rotate plus or minus 45 degrees. Well, one way you might think about doing that is, let's say we had our little DC motor here, and let's say we had a potentiometer hooked up to it, much like we played with last week. We could imagine a situation where when the motor turned and rotated, the shaft on the potentiometer would rotate, connected to the same shaft, and that would give us a really simple feedback mechanism, such that we'd always be able to know where the motor was rotated at any point in time. And for hobby servos, that's exactly how they work. I think the contrast is a little hard to see, but the takeaway from this drawing is you have inside a little hobby servo a high power DC motor. High power, of course, being relative. It's hooked up usually through a gear chain, right? Because this motor is optimized to run at high speed, and what you typically want is low speed and high torque, so you have a bunch of gearing in the middle. You have a potentiometer hooked to the output side, and then you have some control circuitry hooked up to that potentiometer to give you a sort of more direct way of controlling that motor without having to manually read the potentiometer and sort of act on it. There's a way that the servo is actually helping you out, if that makes sense. So actually, I took apart one of my servo motors earlier. Let me see. Here we go. So I wanted to show you what the inside of these guys actually looks like. We might have to smash it with a hammer just to get all the way in detail. Is this as zoomed in as we go? Yeah. So here, let me show you what it looks like before you take it apart. This is what I would call a standard hobby servo. It's about maybe an inch wide, maybe a quarter of an inch thick. And it is designed for use in RC cars, RC planes, home robotics, whatever you want to do with it. It's got this 3-wire ribbon connector coming out of it that we'll talk about in just a little bit. And it has this little dinky plastic gear coming out the top that we'll see how to attach to that shortly. When you pop the top cover off, what you get is exactly what we saw in the diagram, right? So here is, let's see down in there, there is our DC motor sitting inside that circuit board. We have some control circuitry here. We have our gear train on the top, right? That's taking that high-speed motor and stepping it down to something that's lower speed but higher torque. And then if you look down inside there, you see that green thing with the white dot in the middle of it? That's our potentiometer. So as this output shaft turns, I don't think I can actually turn it by hand. Oh, maybe. No, I'm just stripping the gears. That potentiometer is going to turn, and that's going to provide feedback to this circuitry so that the circuitry inside always knows what the position of the servo is. We're not going to necessarily have a way to externally determine what the position of the servo is, but the servo itself will know. Well, that'll make sense, I think, in a little bit. So, in any case, that's the gist of what is inside of a hobby servo motor. So to demonstrate that, let us take a look at our first circuit of the evening. This is our real simple circuit diagram. Oh, and I should say, something that someone requested last week that I think was a really, really smart idea would be the ability to look at all of this code and circuit diagrams either ahead of time or in real time, like if you wanted to try some of this stuff out in advance or play along. So if you go to just down here below, jeff.glash/electronics-bash, and by the time that this video gets archived, I'm going to try that dash out of it, so or either one will work. But if you go to jeff.glash/electronics-bash, you can find all of the code examples, all of the circuit diagrams. I say all. We're going to do some stuff tonight, I'm sure, that goes off script. But the idea is the circuit diagrams and the basic code are on there so that if you're playing along at home, you can read the code, follow along, and reference back to it after the fact. There's also a link in the description of this stream or this video that you can click on to go straight to the page for the stream. So I hope that's helpful. What's happening in the chat here? Jeff turning servos by hand really grinds my gears. We're in for a good night, I think. So here's our basic circuit diagram. The servo, right, has that 3-wire connection we were just looking at. It takes 5 volts and ground and needs 1 digital signal pin to control it. So in our case, I'm using D9. That's arbitrary, right? But the code's going to reference D9, so you'll see what that does. So let's open up our first example of the evening, and we will look at it together. If you're following along at home, this is the Servo basic code that's listed on the website. Let us take a look through the code. We'll assemble the circuit real quick, and then we'll run it all together. So this first line, this hashtag or pound. Wow, I can't. In my mind, just goes to that being a hashtag now. I'm sure somewhere like a 70-year-old gray-haired engineer is crying. We have this pound include in brackets servo.h. That's our way of including the servo library. And we'll go deeper into libraries a little later tonight. But basically that says, hey, someone's already written the code for how to control a servo. Just let me use that code as well. You can include multiple libraries in your code at the same time, but this is saying, hey, I want to specifically make use of this servo code. This next line here, servo, my servo, is basically, it's like declaring a variable, right? We've seen lots of times where we've declared a variable, we've had to give it a type, and we've assigned it a value. This is the same idea, except instead of declaring a variable, we're declaring what's called an object, right? But the syntax is exactly the same, right? I'm saying, hey, this label, my servo, is going to be a servo object. And because we've told the code that we're using our servo library, this word servo has been color-coded with us to let us know that the IDE, the code writing software, knows that the word servo means something. There's also a nice note from this example. Up to 12 servo objects can be created on most boards, which is true. The Arduino Mega and its variants give you a few more. They can be on any of the digital pins. Let's just double check the chat here. FYI, the servo could be given voltage from an outside source if you have a lot of servos. Yes, Chris, we'll get to that certainly in a little bit, and current limiting on the Arduino for sure. So we've told the IDE we want to use our servo code. We've told it that the name for our singular servo that we'll be using is myServo, right? In our setup function here, we're going to do this very important step, which is myServo.attach9. So we haven't gotten super deep into how to use objects within code, but basically this is saying, this is what's called using an object method, which is to say, hey, this object that we declared, myServo, has an action that we can tell it to do. We can say, hey, myServo, please attach yourself to pin 9. And actually, it says it in the comments here, attaches the servo on pin 9 to the servo object. Calling methods from various objects or using the methods of objects is sort of a deeper concept that I won't get super deep into tonight. But if you're just playing with this around, like this is the syntax for saying, hey, servo, please be on pin 9. Make sense? Cool. The loop itself that we're working with to start with is very simple. We have this myServo.write function, and it takes a value between 0 and 180 degrees, and it will rotate it. The servo will rotate itself between 0 and 180 degrees. I think 0 is counterclockwise and 180 is clockwise. If I'm wrong, we'll see it on the table in just a second here. So it's going to go to 0, 90 degrees, 180 degrees, and wait a second in between each one. Sound good? Let's build our circuit real quick, and we'll try that out. For the purposes of this evening, I'm going to be, working with our little hobby servos here, but I'm actually going to make use of a little servo stand that I 3D printed earlier today. This is part of my 3D printed moving light project that I'm so very delinquent on. I will make sure that the link to this piece of hardware is on the description to this video and on the website. It is not yet, but it lets you do useful things like screw your servo in place so you can work with it. And we'll look at the hardware connections for servos in just a little bit. Chris says, look at the servo from which direction will determine direction. Chris, I'm not sure I understand. So I've got, let's zoom ourselves out a little bit. There we go. So I have my servo here. I have put a little bit of extra hardware on it so we can see which way it's rotating. And I'm going to make our connection. So these servos, we said, have this 3-wire connection. And this is a pretty standard color coding for all servos. If we take a look back at our circuit diagram from earlier, I actually included the color coding here. 5 volts is red, ground is brown, and your digital signal pin is the yellow. And this is not the order that they're arranged in. They're arranged in a specific order for a specific reason. They are arranged such that the power pin, the power wire, the red wire, is in the middle. So if you accidentally plug in this connector backwards, you've just reversed the signal and ground pins. So while it won't work, you're unlikely to damage anything. It's pretty clever. So what I will do is I've got my DuPont wires here, my little breadboard wires just shoved into the end of this connector. I'm going to take my brown wire and hook it up to ground. I'm going to take my red wire and hook it up to power. And I'm going to hook my orange wire into digital pin 9 on my Arduino here. There we go. And I'm going to upload our code. Let's see if I've broken anything. It's possible. I was plugging and unplugging things a lot today. I sure have. There we go, COM11. This is a problem updating to board. It's always good to check that in your tools menu, that your port is set correctly, and that your processor, so on my board selection here, I have things set to Arduino Pro or Pro Mini. It's important that I have it set to Uno. Let's try that again. Compiling, uploading, there we go. So now, there we go. So we can see that we're starting from 0, 90, 180, and back to 0. So in the case of this servo, 0 is, I guess, clockwise. And you'll see, and this is true of a lot of hobby servos, right? If we look at it sort of straight on from the camera, it's not quite 180 degrees of travel. It's more like 170. And that's not surprising to me at all. That's pretty standard. These servos are dirt cheap. Like, you can buy a pack of them on Amazon. I think there's one linked in the description. It's like 10 for 18 bucks. They're really dirt cheap, and they get cheaper if you're willing to wait on shipping. So like the fact that they are like not quite 180 degrees, it's not really what you're paying for. When you're building a more robust thing and you want a little bit more quality, you might buy something, a little bit beefier, right? This is I don't know, what is this? A MG996R digital high torque servo. Exact same connector, exact same idea, but with metal gears and higher torque and more reliability. But in any case, there's our servo doing its thing, right? Going from 0 to 90 to 180. It's important to note, so we said just a moment ago that the the feedback inside of a servo allows the servo to know where it is and to put it in the right position that you ask it to be at any time. We don't actually have any feedback path from the servo to the Arduino. There's not a direct way with this servo of saying, hey, Arduino, where is the servo? And that's important because if you're getting into this, and I encourage you to, you will see in the documentation there is also a function called servo read, or myservo.read in our case. This is just a little warning. That read function is not asking the servo itself for position. It's actually asking itself internally what the last value that you wrote to the servo is. Right, so their software will be tracking like, hey, the last time I, wrote to my servo device, I said it was 180. In this situation, like if I were to do on a serial port, serial.println, myservo.read, I would get back in this situation 180, even if that servo had, been pushed out of position or taken to the wrong place in the meantime. So little word of warning there. It's sort of speaking of knocking servos out of position, let me show you, well, we'll get to that. We'll get to messing around with these things a little bit later and abusing them some. But that's the basics of servo control. You give it a position between 0 and 180 degrees, and it just moves there. Kind of amazing. Yeah, shout out questions whenever you have them. Part of the point of like limiting our scope a little bit is to just be able to sort of respond to things and play around a little bit more. Chris says it's important to know where the servo thinks it's at 0 when connecting it to mechanisms. Yeah, for sure. If so, you wouldn't want to say, imagining what kind of things Chris might be running into. Let's say this servo was going to pull a little linkage that was going to drop a lot of confetti on the stage. You wouldn't want to assume that 0 is this way, plug it in and find out that 0 is that way. It's always worth testing, even if you're buying like servos from the same distributor, right? It's always worth testing. Well, let's move on to our next example, and we'll shout out questions when you have them. This will, I think, let us do a little bit better about like showing what happens when you abuse a servo. So for our next example, we're gonna change our circuit diagram just a little bit. We're gonna add a potentiometer. You recall that we used potentiometers last week to do some analog input to our device. So this is the circuit I'm going to build now. Our potentiometer is gonna go on each side from 5 volts and ground, and the center pin is gonna go to analog pin 0, just like last time. For those following along at home, this is the knob demo from the website. This is actually just a built-in Arduino example. I think I encouraged you last time, but if you haven't, it's really worth digging through in your file menu of your Arduino RDE, going into your examples. There's a lot of really useful examples in here, including examples for, if you scroll down a little bit, I know it's a little hard to see on the screen there, examples for all of the libraries, all the extra code you've installed. And we'll look at how to install libraries later. But in our knob example here, well, here, I'll build the circuit. I think it'll be pretty self-explanatory, but we can take a look at the code after that. I'm going to unplug this so the servo stops running around on me at the time. And I'm going to plug in our potentiometer. So just like last time, I'm going to plug in the 2 outer pins of the potentiometer to power and ground. It does not really matter which, only that if you, it will affect which way is positive rotation, so to speak, and which way is negative rotation. If you get them reversed from the way you like them, you can always reverse those wiring connections. So we'll connect the middle pin of that potentiometer to analog pin 0 there. All right, so that'll be our circuit. All right, we'll plug this back in. We'll upload our code, and then I will show you, we'll walk through the code and see how it's doing it. Let's make sure that uploads. Seems good. All right, so now with my potentiometer here, let's get that. Yeah, as I spin that potentiometer, the servo moves to track. Right, so you can see I spin this all the way clockwise, the servo moves all the way clockwise, I spin it counterclockwise, the servo moves all the way counterclockwise. Sort of very, very rudimentary remote control, even if remote is like 4 inches apart at this point. Palmer says, in your experience, even though the exact rotation may not be the correct degree, is repeatability generally accurate? Yeah, repeatability generally is. You can be somewhat limited, this is a little bit of a rabbit hole, by the resolution of the servo communication protocol itself. Let's go down this rabbit hole, because we were going to get there anyway. Which is just to talk a little bit about how the Arduino is actually sending the positional information to the servo. So when you hook up your servo to your Arduino, you have your power, your ground, that's easy. That single digital line is sending signals in the following format. You are doing essentially a version of pulse width modulation, which we talked about last time, right? You're sending pulses at a specific regular frequency, and the width of them is going to vary. And the standard for servo motor control, at least for hobby servos, is if that pulse is 1 millisecond long, then the servo should be at its 0-degree position. If it's at 2 milliseconds long, it should be at its 180 or its full rotation position. And anywhere in between, it should sort of scale linearly between those two values, right? So if we were to take a look at our signal line as we were controlling the servo, or going from 0 degrees to 180, we would see that pulse go from 1 millisecond to 2 milliseconds and back as we rotate through. Here's just a slightly more involved diagram. There's about 20 milliseconds. It's about a 500 hertz frequency that it's oscillating at. This basically is saying the same thing in a slightly different diagram, a little bit more to scale. The reason that this goes back to your question, Palmer, about repeatability is what you are fighting in terms of repeatability, right? Your little tiny, inexpensive circuitry inside of your servo has to be able to distinguish small increments of time to be able to distinguish its position. And for circuitry, that is as low cost as it possibly can be, your maximum resolution is not particularly high. On these guys, it's about a couple of degrees, which is to say that even if you could generate a pulse with a very, very specific timing, let's say 1.11962 seconds long, this circuitry is not going to really be able to distinguish between 1.11962 or whatever I said, 1.12 seconds long. Normally you have about sort of 200 different positions that this can occupy, or maybe 100. It's not super high. Of course, higher quality servos and these new things called digital servos, which we won't super get into tonight, can have some more specific and repeatable variability. But for how cheap these things are, you will always get back to the same place, but the same place might be plus or minus a degree or two, if that sort of makes sense. Yeah, a little bit of a tangent, but I think a tangent we were going to go on regardless. So thanks. So just to take a little quick look at the code for our remote control servo example here, let's jump back over. This is the knob example we said from our code, right? So it starts out exactly the same way as our other code. We include servo.h. Servo.h, by the way, is a file that lives on your computer. You can look at it if you want to. It's just, when you think about the words library, the servo library that we're using, library just means somebody else's code that they wrote for you. You can make use of to do things in your code with. So anyway, getting ahead of ourselves, right? So we've included our servo library. We've declared an object called myServo again. We defined our analog pin, our pot pin, to be 0. And we've created this variable called val, just to hold the value of the analog pin for us. In our setup function, we've done myServo.attach to pin 9 once again, right? So that attaches our servo object to digital pin 9 on the Arduino. And then here's where the magic happens in the loop. And some of this should look familiar from last time, right? So we're going to do an analog read on our potentiometer pin to get its value. We're going to use our favorite function, the map function, because, of course, analog read generates a value between 0 and 1023, you remember from last week, and we want a value between 0 and 180. So we will use our map function to say, hey, wherever we are in this range 0 to 1023, map that onto the range 0 to 180. We write that new value out to our servo, and then this is a good catch. This piece of example code delays for 15 milliseconds after doing it. There is, as you will have seen on the example on the table, there is nothing that says that when you change the position, the servo gets there instantly. So as you're thinking about, sequences of movements, with a servo, it's good to remember that the servo is going to take a little bit of time to actually get there. So if you're thinking about this for animation or mechatronics or something like that, you do sometimes have to account for the fact that even though you say, hey, servo, go to 90 degrees, it's not going to get there instantaneously, right? So that's the basics of our knob control. That's great. Now that we sort of have the fundamental building blocks, I would say, of digital input and output and analog input and output, that really frees us up to sort of start making use of some of these controls to build fun things with, which I like a lot. This is a good time, I think, to show you what happens if you if you impede a servo's movement, right? So I'm going to take this potentiometer, I'm going to spin that servo all the way to the right, I'm going to hold this servo in place, and I'm going to turn the knob back to the left. And I can feel this pushing against me, not particularly strongly. We could look at the data sheet for it and figure out, specifically how much force it's able to apply with a moment arm of this length. But the important thing to know is, even though I'm impeding it for now, because the signal that's being sent to this servo still says it should be in a specific position, it in some sense knows where it should be. And so when I release it, it will go to the correct position. Let me show you that again. So I'm going to hold the servo in place, I'm going to turn the knob all the way the other way, and when I release, the servo will go to position, right? This is why it's good to remember that while the servo is being told to go to a specific position, the Arduino itself doesn't really, for these servos, have a way of knowing whether the servo has actually made it there. It just knows what it's asking the servo to do. So if you're thinking about some kind of robot or mechatronics or something where it's important that you actually have reached your final position, remembering that just writing to a servo to tell it to go somewhere is not sufficient to guarantee that it actually gets somewhere. There are servos that that do have a fourth wire, a positional feedback wire, that basically takes, that little potentiometer that's doing some sensing down inside there and brings that center connection out on a center wire. Servos with feedback, right? Direct feedback. And you can use that to sort of cross-check in your code, say, hey, go to this position, and then later check, hey, did we actually make it to that position? And if not, that might tell us something. There are also other ways, of course, of telling whether a thing has rotated or a thing has moved to a specific place. There are just ways of doing that within some specific servos themselves. Yeah. So that's the gist of basic servo control. PF Janky says, do the motors home themselves when they power up? Yeah, for sure. And if you think about what's happening inside an Arduino, right? When the Arduino boots up, and we'll do this in a second here, it's going to read the position of this potentiometer, and then it's just going to start sending the appropriate signal to the servo motor itself. So no matter where that servo starts, it's going to end up in the right place. And here, I'll show you that. So I'm going to rotate this all the way clockwise. I'm going to remove power. I'm going to rotate this all the way counterclockwise, and plug this back in. And when I do, it moves to the right position. Super handy. Yeah. It's super fun. I think this is the first thing that we talked about that involves physical motion, which is kind of fun. I was talking to a friend online the other day who was looking for some resources to get into animating some puppets. I was like, well, come here Sunday night. We'll be making things move. The ease with which you can attach a servo to an Arduino, I think, makes them really approachable for basic hobby projects, RC projects. They're a cool place to start because you can start moving things around, which is fun. Now that we have a thing that moves, I think this is a good chance to do just a little bit of a digression into randomness, because it'll be more fun to show randomness, I think, with a little moving device than it will with just a blinky light, because we've done blinking lights for a couple weeks. PF Jenkins says, I made sound waves move last week. I also made photons move, I suppose. But this is more of like a making things podcast. Good God. I spent about 4 hours on watching a live stream last night of some people podcasting, and now that's all my brain can think about. This is more of a making things stream and not a physics stream, so I think we'll stick with my definition of moving things. Randomness. Let's talk about it. There is essentially one function that you can use to introduce randomness into your code. I suppose there's one function and there's a setup type function. So it's up to you how you use it, but let's look at how that works. This will be, for those following along at home, this will be the servo random example from the website. And it's going to look very similar to the code we were just looking at, right? So we include servo.h, we declaim our servo, we attach a potentiometer, we have a value variable, we attach my servo to pin 9. Here's the first of our new functions I'm going to gloss over for a second, and I'll come back and tell you why it's important. Random seed analog read A1. Put that in your pocket. We'll come back to it. Here's the money. Inside our loop, I'm going to do this. I'm going to take my value is going to equal random. And actually, let's start with random 180, which I think is what the example code has, which will create a random number between 0 and 180 inclusive? I think inclusive. In many languages, the random function is not inclusive of that upper range. Someone can check me on that. So I'm going to generate a random number between 0 and 180. I'm going to write that number as the degrees to my servo. And then I've actually used random a second time. I'm going to delay a random number of milliseconds, let's say between 500 and 2000. So here we see two different uses of this random function. If you call it with a single input, a single number in this case, it will generate a random number between 0 and the number you provide. If you provide it two numbers, it will provide a random number between the first value and the second value, right? So in this case, between 0 and 180, in this case, between 500 and 2000. So if I upload that, come back over here. I guess I'm not using the potentiometer in this code at all, but I left it in there. You can see every half a second to 2 seconds, it picks a random direction and moves to it. That's randomness. So when you're using the random function, Chris has a random number between min and max minus 1. Yeah, so I guess this code is generating a random value between 0 and 179 and not 180. It's a good catch. So all the randomness you have is to generate a random number, and how you choose to use it is up to you. In this case, we're using it in two different ways, right? We're using it to determine a random position, and we're using it to determine a random delay time, which are sort of two of the more common ways to put randomness or random behavior into your code. You can feed that random number into anything. You could feed it into an analog write function and do a random dimmed value. You could feed it into a digital write function and do a random digital value. Actually, let's do that example, because I think it will be interesting. We'll just start a new bit of code. This is, how I said we were going to sort of go off script sometimes. Well, this is one of those times. We'll declare a new variable called LED pin. We'll just use our built-in LED for this example, I think. In our setup, we will declare it as an output. And then in our loop, we'll use some randomness. And actually, I'm going to include that same mystery function that I told you not to worry about in the other code in this code, so I can talk about it. Random seed analog read A1. And then in our loop, I'm going to say int random thing equals random 0. Let's do this. 0, 1. If random thing equals 0, we will digital write to the LED pin high, right? So there's a 50-50 chance. I guess this should be 2, right? Because we want to generate a 0 or a 1, and that's what this random function is going to do, right? And else, if random thing is not equal to 0, digital write LED pin low. And then we will do that, I don't know, we'll do that 4 times a second. I think we'll be able to see that. Oh, what do we call this? Blink test. We'll save that. We'll upload. Come back to the table. Probably have to shield this so you can actually see that built-in LED. You'll see every quarter of a second, it's basically making a random choice as to whether to turn that LED on or off. This is a good way to start thinking about influencing the possibility of something happening randomly, right? Because right now our call to that random function generates a 0 or a 1, and it'll do it with roughly equal probability. I say roughly because what is true random in this universe? But essentially, right, you'll have a 50-50 chance of turning on or off every quarter of a second, right? And you can sort of see that that's what's happening here. It might be on for a little while and off for a little while, but on average, it's about the same. What if we wanted it to be on 80% of the time? Well, we could modify our code, right, to say something like, let's do this. Let's do a random number between 0 and 100. And we will say if random thing is less than 80, digital write LED pin high, else digital write LED pin low, right? So in this slew of random numbers between 0 and 100, there's an 80% chance it will be less than 80, and if so, it should be high. If not, it should be low or off. Right? So as you're thinking about introducing probabilistic events into your code, that's an easy way to do it, especially if you do it out of 100, because then the numbers that you're putting into your code really do directly relate to probabilities. Right? So now you'll see, though that light is occasionally off, it's on about 4/5 of the time. I don't know how easy it is to grok 4 out of 5 times it's on, especially without a marker in between, but that's the gist of probabilistic random behavior. So that's the gist of the random function. Now we have to talk about the random seed function I said earlier. So as I alluded to a moment ago, what truly is random in software, right? Our code doesn't genuinely have a way of doing a random physical process like rolling a die or flipping a coin. It only has a mathematical function that in the long term generates values that are something like random, but it really is a mathematical function, right? It's a deterministic process that starts from one place and then generates the next random number and then the next random number and so on. What you really want is for that random function, which has millions and millions of possible places it can be sort of in this loop of random numbers, to start at a more or less random place. And that's what this random seed function is doing. It's saying, hey, I want you to start your algorithm at, I don't know, position 500 or with input 3197, whatever you want it to be, right? That gives it a starting place for this algorithm, and that will let your outputs be truly random. Now, if you seed it's called, seeding your function, giving it this input to start with. If you seed it with a consistent value, you will always get the same sequence of random numbers out. If I say my code as a random seed 666, and let's demonstrate this. Let me, instead of digital right here, let me do a serial print line. Let's do serial.begin 9600 that we remember from last week. I'm going to say, and each time through my loop, I'm going to generate a random number. I'm going to print it to the serial port.
One moment. Sorry.
Siri just started talking to me. I don't know. Maybe she thinks her name is Serial. So it just freaked me out. I thought someone... it's all right. So each time through our loop, I'm going to generate a random number between 0 and, let's do 0 and 100. I'm going to print it to the serial port. I'm going to delay for 1 second. Right? And this is with our random seed being 666. So I'm going to upload that code, right? And once it's uploaded, I'm going to open our serial port and make sure my baud rate is consistent, which it's definitely not right now. 9600, we'll have a new line. I should say, I don't think I mentioned last week, every time you open the serial port on a serial monitor in the Arduino IDE, your program resets. So it's not a super easy way to monitor the ongoing process for code, because when you open that serial monitor, you reset your code. So just keep that in mind when you're using it. In any case, let's look at our first few numbers here that came in through the serial port. 36, 19, 7, 71. Now, if I'm not talking out my butt, the next time we run this code, we see a little bit of leftover from the last time the code ran. We have 36, 19, 7, 71, 63, and so on. Right? If I close this again, open it up, yep, we have 36, 19, 7, 71. If I press the reset button over here, right, we'll reset. We'll probably get a little bit of garbage to start with. 36, 19, 7, 71, right? Because this algorithm that's simulating randomness is always starting in the same place, it's always giving the same sequence of random values. Now that can be useful, right? If you are trying to troubleshoot a really tricky problem and your code has to do with randomness, sometimes it's nice if that random type stuff is actually very predictable. But for a lot of the times, you don't want that. You want something closer to true random. And so what we do is, instead of feeding a value to this random seed function, we give it a value that is, in some sense, physically random. And in this case, it is taking an analog reading of a pin on the Arduino, an analog pin that is not connected to anything. So its voltage could float anywhere between 0 and 1023. And because it really could be anything, it's not hooked up to anything, it's sort of based on, I don't know what, free-floating static charges or dust particles or gas in the air or who farted recently or I don't know what. This will give you a pretty decent approximation to something being truly random. So always a good thing to do if you can. Starting with a specific random seed in your back pocket, a good thing to know about for troubleshooting. So that's the gist of random. Let's see what's happening in the chat. This is how many map generation seeds work. Yeah, oh yeah, Kenneth's alluding to. So if you have a game that generates a more or less random map. Minecraft is a good example, right? When you start a new world in Minecraft, it asks you to provide a seed, or it'll generate one for you, and it will take that base number or phrase or however it wants to compute it and use that as the basis for a deterministic algorithm, right? A predictable algorithm that in and of itself produces sort of unpredictable behavior or very different behavior based on what that seed number is. But it guarantees that every time you start with that same number, you get the same results. Similarly, that's what our code is doing. It's saying, I'm going to determine output that's going to be hard for you to predict, but it will be known. Yeah? Cool. That's randomness, more or less. Palmer says in the chat, and I'm grateful for it. Who farted with parameter Jeff? That's, well, maybe not a great segue, but a decent segue into talking just a little bit more about libraries, because we've been using this Servo library tonight, and I haven't really explained what that is or how to use it. So let's talk a little about libraries. I said earlier, a library is really just somebody else's code that we get to make use of. There are many libraries that come included. When you download the Arduino IDE, the programming software, you get them for free, basically. They come along with. Here, let me start a new bit of code, and I'll show you how you make use of them. So your libraries that are currently installed, if you go to your Sketch menu and go to Include Library, you get a list of all of the libraries that come with your Arduino software. And it's probably a little bit hard to see on stream, but you can play around with this for yourself. I've got Bridge, EEPROM, Explorer, Ethernet, so on and so on. I've got Servo down here. I've got the Stepper library that we'll use in a little bit, and so on. And additionally, any libraries that you have added to your Arduino IDE, and we'll see how to do that in a second, show up down below. So if you are starting to code and you need to make use of a particular library, the Servo library, you can come into Sketch, Include Library, and just click on the library of your choosing. So here I'm going to click on Servo, and you'll see it does the including for me, right? Let's say this sketch also needed to use the Wi-Fi library. Now, this Arduino doesn't have Wi-Fi code. It doesn't have any Wi-Fi hardware built into it, so it wouldn't run very well. But if I were to click Wi-Fi, it will include all of the necessary bits of code that are going to make that Wi-Fi library run. So this is how I recommend you include libraries into your code. You just come to the Sketch menu, do Include, and then click on, in this case, click on Mouse, includes mouse, and make sure it gets all of the verbiage in here that you need. What if you're looking to use a library that's not included with the Arduino IDE? Well, there are a couple of different ways you can do that. If you come back up to your Sketch menu and do Include Library, there is a thing called Manage Libraries right at the top. And if we click on that, and we'll see how visible this is. There we go. You get the Library Manager, which pulls a list of many available libraries from many possible sources. So in our case, let's say I wanted to use a touchscreen. I might search touchscreen, and my first result here is the Adafruit touchscreen library. Well, that seems pretty decent. If I click on more info, it will take me to the Adafruit website where I could learn, what does this library do? What might it, is this the thing I need? If I were to say, oh, that sounds pretty good. Here, let me, Adafruit touchscreen library. If I just hit install, we'll see we have a little progress bar down here. It updates this list, and then it's installed. And then when I come back to my Sketch menu and say Include Library, down here in my Contributed Library section, I have Adafruit Touchscreen. And when I click that, I get include touchscreen.h. Simple as that. The other way to add libraries to your IDE that didn't come with them, let's say for whatever reason, and there's lots of them, that someone built a library and put it up on GitHub, right, where they might store some of their code online, and it's not something that's been cataloged by the library manager in the Arduino IDE. Let's go and find one. Let's say, here, let's pick a different Adafruit library, because I used touchscreen already. Let's say this Adafruit HX8357 library. Is something I want to use. Yeah, I want to make use of the HX8357. It's a great product. It's so much better than the 8356. I don't know what it is. But let's say it wasn't being cataloged by the library manager. Here's how you would add it. On GitHub, at least, I would come to clone or download over here on the right-hand side. It's clone or download. I'm going to download the zip folder of all of the code that's included with this library. Right? Once it finishes downloading, I come back to my IDE. In my Sketch menu, I go to Include Library, and second from the top, at least on my version, it says Add Zip Library. I'm going to navigate to the place on my computer that has that zip file that I just downloaded. In my case, it's in my Downloads folder. What was it called? HX? Adafruit HX8357 Library Master. I'm going to hit Open, and that will have included that library here into my contributed libraries. So I come down to contributed libraries, say HX8357, and now it's included in my code. So that's how you would add a library if it's not cataloged by the library manager. And a lot of them aren't. I'm not, to be honest, I'm not entirely sure where that library manager pulls from. It has basically all of the Adafruit ones are on there, and a lot of other ones from third-party developers, but of course it's not cataloging all of GitHub, so I'm not sure what its master list is really pulling from. But downloading the zip of the full library and including that in is always a great way to go. It's also worth knowing, once you've done that include zip folder sketch, the IDE is making a full copy of that library into your local path, your local documents, basically. So you can go ahead and delete the zip file itself once you've included it into your IDE, because all the code is also stored elsewhere, if that makes sense. There's libraries for all kinds of things, y'all. This is one of the wonderful things I think we talked about in week 1 that's great about Arduino, because it is the most popular platform on the planet. If you can think of a thing that you might want to do with Arduino, there is a decent chance that someone has done something pretty similar, and if you're lucky, has maybe written a library for at least the basic part of it to get you started. There's a library for talking to touchscreens, digital displays, potentiometers, rotary encoders. Just to look at the libraries that are available in the IDE here. Robot IR remote, liquid crystal displays. Some of the ones I've downloaded in the past: IR control, Ethernet, a DMX control library, all kinds of things. SACN, NeoPixels, like, people have done a lot of work on this stuff, and so as you're starting to develop, a more intense use of the Arduino, it's worth looking for a library, because it really can save you some time. Let's just check out the chat real quick and see what's going on. Chris says, can also take the GitHub link and add it to the preferences. Interesting, Chris. I didn't know that. So you can just take the GitHub link itself and add it into the library manager? That's really cool. I learned something tonight. I've always just downloaded the zip file and included it that way. Kenneth says, its odds are also very good that the library was not well written, so you might need to dig into it and start editing it. That is super true. It's worth sort of verifying that the library is doing what you want it to do. I'll give you a story. I was writing a bit of code for Lee and Travis, who may or may not be here this week, but they were for a time involved in the lighting department at the Santa Fe Opera, and they were looking for a device that would read a piece of lighting data off the lighting network, read a specific SACN value for those who know lighting data, and display it on a little 2 by 3 inch screen for their spotlight operators to use to see what the level of their spotlight was at. And I found a really useful library called LXDMX that I used to sort of make the core of that product. But the problem was there was a very sort of there were two issues. One, it wasn't sort of handling all the proper edge cases for some of the types of lighting data that you're allowed to put on a network, but really, no one really does except a few manufacturers. And of course, some of the manufacturers they had in-house did. And it also had a very subtle bug in the code for handling multiple sources of lighting data at once. It was pretty well written. It would say, if I'm seeing, this channel should be at full according to this source and 50% according to this source, I'm going to do highest takes precedence and say that it should be at full. The problem was when it had a third source that was in between the other two, it would default to that intermediate source instead of that highest level source. And so I had to ultimately go back in, edit the code, sort of fix that bug before it was actually functional. So a long way of saying, don't necessarily trust your libraries just because you can download them. Oh, Travis is here. Oh, and those boxes are still in use. Oh, I'm so glad. That's super cool. I'll see if I can dig up a picture of one for next time, because that was a super fun project. Lee and Travis put together a really neat 3D printed case, which is always a nice accompaniment to a finished Arduino project. I sort of figure, whenever we get sick about talking about Arduinos, which maybe never, 3D printing would be a super fun thing to sort of accompany this series. All right, we talked about libraries. We talked about analog control. Oh, I want to talk just a little bit about how you actually connect to a servo in terms of the physical connections to the device. So, just in case you haven't worked with one before, I'm going to make use of my 3D printed mount here. And again, I'm sorry I didn't put this up beforehand, but I'll make sure it's online after the fact. I'm going to take my servo here. Let's get ourselves a little zoomed in. Basically, all hobby servos that you can get off the internet come with the same kit of parts. You get 3 screws and 3 or 4 arms, depending on the manufacturer. You get these various arms with various holes in them. There's a little halfy one, a little double-sided one, and this X-shaped one. And you'll notice they have little tiny holes in them, and that's because they're sort of intended for use with the remote-controlled vehicle market. So what you're intended to do, right, is either use it for rotational control, or maybe you hook a bit of wire or a linkage through that and use this to pull something back and forth. right? So for our purposes, let's use our X-shaped one here. This is going to be a pretty tight press fit onto our plastic gear on top of our servo. And I'm going to use my smallest screw. Just going to slip right down in there. The inside of these arms is a little bit ridged. It's meant to interface with that plastic gear, but the tolerances are usually so bad that you're relying on the flexing of that plastic to make a really good connection. And that can be a challenge if you're, say, trying to interface this to a 3D printed project. Getting that tolerancing right can take quite a bit of time. This, I shall say, I was pretty casual about doing that attachment step there. Of course, I don't have any idea where in its rotation that servo was without rotating it. So right now, 180 degrees is all the way this way. Maybe I wanted it there. So I'm just going to loosen my screw. Now that I know it's rotated all the way clockwise, I'm going to pop my arm off, set it back to sort of square in line there, and then use my screw once again. These cheapo hobby servos won't stand too many times of connecting and disconnecting, just because the plastic on the gear on the servo itself will get stripped. But I think it'll stand up to 2. So we'll screw that in. There we go. Yep. And then to attach it to a physical device, you'll notice I have these 2 holes just there in the side mounting tabs of my servo. At least from my mount, those are going to match up with a couple of holes I've put in my mount here. And then I'm going to use my 2 larger screws to just screw those into the plastic, hopefully. And if I remember right, I'll do it where you can actually see it. Chris says called servo horns. Yeah, these little arms, servo horns, is another probably more common name for them. Let's see here. Let's screw that in. You can watch my hands doing a screwdriver. That's the thrilling internet content that I know you join us for every week. This other side. The mechanical interface of these servos really, I think, is probably the hardest part about integrating with them with a product or with a project, just because these sort of semi-recessed mounting arms are not the most intuitive things to mount to. So if you have to make a bunch of something, I recommend coming up with sort of a standardized interface for them. If you're integrating with an RC car or something, it will probably already have the appropriate mounting positions for it. So there we go. So now we have our servo mounted in place and ready to rock. Yeah, that's about all I think there is to say about hobby servos for now. Shout out questions if you got them. But in the meantime, I'm going to take a sip of my Little Crazy and just enjoy the progress that we've made so far. Oh, very tasty. I think I say that every week, but we haven't had a bad beer in the house in a long time, so I feel very fortunate about that. Keep thinking about questions. I know there's a little bit of delay. PF Janky said, did you include the screw holes in your 3D print or drill them? I included them in the 3D print. I actually included them a little bit undersized, just so that the screw still has something to bite into. Originally, I had done it so that you had to sort of use the screw to make the entire hole, and I found that I cracked the plastic, so they're included. If you're doing this into like a piece of wood or something, I would definitely recommend a pre-drill. Should we talk about stepper motors? I think let's talk about stepper motors. Slides time. So what is a stepper motor? A stepper motor is a motor that moves in discrete steps. Ta-da! I'm not huge on long definitions. By a motor that moves in discrete steps, so without going deep into the weeds about how motors work, and some of you may be familiar with this already, a motor is a device which has a permanent or semi-permanent magnet inside of it, and by selectively electrifying coils of wire that either surround or are adjacent to that magnet, you can cause that magnet to want to move in a given direction or rotation. I sort of just came up with that description, but I think it's pretty accurate. In a DC motor, you basically have a small device of some kind inside the motor that causes it to connect and disconnect either the singular coil or successive coils of wire to cause that axle to continue to spin constantly in a single direction, depending on the polarity of your voltage you apply. In a stepper motor, you have multiple coils of wire that give you much finer control over how much the shaft rotates at any given point. And I think that these gifts really get the point across. Don't worry too much about the finer details of what's going on, because these are actually showing two very different situations. But you can see, on the left here, this center object here is meant to represent a magnet or a piece of metal with various poles, a sort of tooth structure here. You can see a similar tooth structure here on the right. And as we selectively energize various coils in some orientation around this this multi-pole magnet in the center, we can be very specific as to how far that center piece, that center magnetic piece, rotates with in any given moment, right? For the purposes of this evening, for the pizzas of this evening, I'm not going to get too deep into the weeds as to how stepper motors actually work, because we're going to focus on using them. But as you're thinking about how you're driving these things and why it's a little bit more complicated than the servo motor, this kind of discrete action on your various these various coils is exactly why. So I have one more slide on that. Oh, just an interesting cutaway of a stepper motor, showing again this idea of having a multiple pole magnet in the middle and various coils of wire on the side. There are some different configurations that are important as you're trying to figure out how to wire one up, but we'll get into that a little bit later. So unlike a servo motor that only needed, power and ground in one data line, the connections to a stepper motor are significantly more complicated. So this is the circuit that I'll be working with this evening. If you are starting from scratch and you have a Getting Started with Arduino kit, it probably came with an L293D stepper motor driver or H-bridge circuit. If not, they're cheap and everywhere. I'll put a link in the description to one of the modules that I use. You'll see when we show the circuit on the table in a little bit here. It's got a few more bits and bobs on it. Basically, they put a heatsink on it for me and some protection diodes, which is awfully nice of them, but not necessary. If you build this circuit, it will work. The thing to take away from this diagram here, and we'll look at it on the table in a sec, is our motor driver takes a power voltage. In our case, it will be 5 volts. We powered from, not directly from the Arduino. In our case, it takes these 4 input wires in 1, 2, 3, and 4. In our case, hooked up to pins 8, 9, 10, and 11, although you could pick whichever digital pins you want. And those are going to more or less directly control outputs to 4 separate coil orientations that we have on our stepper motor. In our case, it's a bipolar stepper motor. I think you can see down here, and we'll talk about that, what the difference between a bipolar motor and a unipolar motor in just a little bit. And then the outputs on our stepper motor controller connect, obviously, to the stepper motor itself. So this diagram in the slides in the description, also on the website, jeff.glass.electronicsbash. So go and take a look at this if you're trying to hook this up. So the reason that I showed you that in schematic form and not first on the table is that on the table, it turned out to be a little bit of a mess. So let me clear a couple things out of the way here, and I will bring that over. Zoom out a little bit. We'll get rid of our earlier circuit, and we'll bring in this guy. So what's going on here? Well, this is our L293 based stepper motor driver. And like I say, I bought a module from Amazon. I'll make sure we put a link to it that has it all on a nice circuit board, has some nice terminals that you can screw your wires into, has a nice heat sink so you don't stand a chance of frying it, capacitor for a little smoothing. There's just some nice features in this. But you can see here my 1, 2, 3, 4 wires that are going to the 4 pins on my Arduino Pro Mini. Up until this point, right, we've been using our Arduino Uno. For the purposes of this example, I'm actually going to make the switch to a Pro Mini. The Pro Mini is actually one of my favorite form factors for an Arduino. I have a spare one here we can zoom in on. It has on it an Atmega 328 chip, just like the Uno does. It has a reset button, it has a built-in LED, it has some capacitors. It's functionally very, very similar to the Arduino Uno with a couple of key caveats. All the code you write is the same, right? It's the same processor chip. You can write all the same code, runs at the same speed, just as powerful. The places where it is different, on the Arduino Uno, the thing that is providing 5 volts, if you're giving it a voltage higher than 5, is this big chonky voltage regulator here. Well, decently chonky. On the Pro Mini, it's that little tiny guy right there. So the total amount of power you can provide at 5 volts from the Mini is very limited. And especially if you're buying sort of knockoff models or cheapy ones from the internet, I wouldn't rely on them to pull more than 40 milliamps, 60 milliamps. It's very, very limited. And I have seen these things smoke and blow up many times. But the reason that I use them is because they are small, they are cheap, and you can put these headers on them so that you can plug them directly into a breadboard, which for a circuit that you have many, many wires going to is really handy. So I like the Pro Mini for something that I'm going to do a lot of breadboarding on. The other key difference in using a Pro Mini versus an Uno is that the Uno has on it a chip which handles communication between the Atmega 328, the processor, and the USB side of things, whereas the Pro Mini does not. This basically exposes some ports on the processor itself directly to the outside world via these header pins. And so what you need to talk to your computer is a USB to serial converter, sometimes called an FTDI dongle. FTDI is actually a brand of these, but it's sort of become a slightly generic term. So this has on it our USB to serial converter that we had built in to the Uno. So what you need is as many of these as you can possibly hope to blow up, and one of these to program with, or maybe a couple of these. You can see I actually squanched the pins on this one a little bit. But once you have this hooked up, and we'll plug this into our Arduino here, and plug it into our computer, it will function and be programmable just like the Arduino Uno. So though you're seeing a slightly different form factor, all of the code is going to be the same. Just checking in real quick on the chat. Chriswick says, are we taking bets on if Jeff remembers to change the board type when he tries to program the Mini? Is it cheating if I read the chat in advance and then have a little tip off? As I was doing my sort of rehearsal run for this earlier, that definitely happened many a time. Chris says, what happened to the top pins on the programmer? I threw my programmer into my computer bag a little carelessly, and they got crushed. Is the honest answer. Going back to our what's going on the table here, just briefly. Let's do that view. There we go. So I have my Arduino, I have my motor driver, I have my potentiometer, I have some buttons and things over here that we'll use for some later examples, but I have my potentiometer hooked up to pin A0, and I actually have some LEDs in parallel with the 4 output positions, the 4 output wires going to my stepper motor that we'll be playing with tonight. This is a stepper motor. I'm pretty sure it came from American Science and Surplus, which has a couple physical stores here in Chicago, and you can find them online at AmSci.com. American Science and Google American Science and Surplus. Incredible store, lots of great scientific surplus junk. Really tremendous place. So that I've got hooked in for us to play with tonight. The LEDs are there so we can sort of have a visual representation of what's happening. I am going to, just to make this a little bit easier to see, because I realize that this stepper motor has just a threaded black shaft on it, I'm going to take a little bit of blue painter's tape and make a little flag here so we can see when it actually spins on camera. So, do a quick cable swap. This is the one other thing about, changing from the Uno to the Mini. The Uno has a USB A-type connector on it. Kenneth, correct me if I'm wrong. My USB to serial converter has a USB mini connector on it, not a micro, a mini, which are becoming harder and harder to find, which is kind of a pain. But I'm going to plug my mini cable in here, always in the wrong orientation, of course. There we go. And I'm going to plug my USB cable into my computer side here. We'll see that Arduino lights up. That's a good sign. USB-B, yeah, I was close. So there is our setup. I know it's a bit of a mess. Go back and reference that schematic diagram. I'll tell you exactly what's going on here. Let's look a little bit at some code, and then we'll fire this thing up. For those who are playing along at home, this is the motor knob demo. Let's see here. Come over to the computer and find motor knob. Yeah, here we go. And this, again, is just the motor knob example from the Arduino IDE. So if you go to examples under stepper examples, this is the motor knob. So much like our previous code, it's going to start with our include stepper.h. We'll use the stepper library. So here we have a new thing we haven't seen before called define. You can think of define for most practical purposes as much like defining the value of a variable. It's going to say, hey, let this symbol called steps be equal to this second value, which is this, in this case, is integer 100. The slight difference between define and actually defining a variable is and this is a very hand-wavy explanation, but more or less by saying define, we're going to let this processor say, hey, this thing called steps, we are never going to change throughout the value of our code. In fact, we're not allowed to change it. And so anywhere you see steps, as you're thinking through how to program this onto the device, we don't need to think about that as a variable. It can literally be the hard-coded number 100 in this case. So that may save you. It prevents you from changing this value later, but for things that aren't going to change, like in this case, the constant number of steps that makes one full revolution of our servo, we can just define this at the beginning of our code. Yeah. Coming down a little bit here, I think this value is the default value and is not correct, but if it's not correct, we'll find out in a second here. We come down to here, where we're declaring an object, like we declared our my servo earlier, where we declare a stepper object now called stepper. The stepper initializer, right, the thing that's going to create our object, in this case, takes 5 values. It takes this value steps, the number of steps that causes the motor to rotate one full revolution. And by steps, I mean, I guess I should clarify, when we're changing the voltage on those individual coils in our stepper motor, there's basically a certain minimum amount that we can cause the motor to move as it rotates, and that minimum amount is 1 step. Common values for steps to rotate a continuous, one full 360-degree rotation are 24, 48, and 200 are pretty common. I think mine is 400. So I'm actually going to change that right now. If we're wrong, well, we'll see in a sec. The other 4 values here are the digital pins on your Arduino that the stepper motor is hooked up to. In our case, hooked up through a stepper driver circuit. But so we have our steps value 400 and pins 8, 9, 10, 11. We're declaring an integer called previous, which we'll make use of in a second here. In our setup function here, so we don't have to do we don't have to do an attach step like we did with servos, right? Because we already told it what pins the stepper motor was on. But we do have this set speed function. We do stepper.setSpeed 30 RPM. Much like we called the method of the myServo object earlier, we're going to do stepper.setSpeed to say this stepper object, hey, set your speed to 30 revolutions per minute. Cool. So that's our setup part. In our loop function then, we're going to read the value of the potentiometer attached to pin A0. And if I don't think I mentioned this last week, if you're doing an analog read, it assumes that you're only going to do that on an analog pin. So we don't have to say analog pin A0. We can just say pin 0. It assumes you mean analog 0 in that case. And then we're going to take that value, we'll subtract our previous value to basically see how far the potentiometer has moved since the last time that we went through our loop, and then we're going to move that number of steps in one direction or another. Yeah? So let us change our board type. So those who had the pool for Jeff forgets to change his board type, you have to drink now. I'm going to change this to Arduino Pro or Pro Mini. I'm going to double check that my port is still right. I think it's port 4 now. The other COM port is my tally light setup that I have on top of the camera. But if this doesn't upload, we'll know why. Looks like it's uploading. Yeah? Good. That worked out very well. So now, let's see. Let's see if I've wired everything correctly too. Let's see. Why are you not? 400 might also be the wrong number of steps. So let's just double check here. So I've got this hooked into 1, 2, 3. I don't think I've tested it with this potentiometer. It's probably possible I have a dud potentiometer that doesn't work, in which case it'd be an easy fix. Let's come back over to our code just real quick and reset this to 100. Come back to the table. While I'm troubleshooting this, I'll look at a few questions from chat. Let's see. Wanted to find the steps as 360. I think I've answered this question now here, Travis, but the steps variable is the number of steps it takes to make a complete rotation. It's potential that it's bad. Drive ahead requires a pin order 8, 10, 9, 11. Yeah, for sure. This particular motor hooked up in this way took the pins in order 8, 9, 10, 11, but that was sort of by chance. I could always, could reverse the wiring of them or reverse the motor connection or something like that. The 8, 9, 10, 11 is not specific to this motor in any way. Wow, that doesn't work at all. That's the first, I was gonna say this is the first demo we've done on this stream that just doesn't work at all, but I somehow think that can't possibly be true. I'll tell you what I'll do. Let me upload another bit of code. I'm sorry for the jiggery pokery. Upload another bit of code that I know was working early. Oh. I figured it out. Before I reveal what's gone wrong, does anyone in the chat want to take a guess as to the thing that I have forgotten to do to make this setup work? Taking any bets? This is the hilarious thing is, like, if I was gonna have joined a pool for what I thought it wasn't going to be, but I was going to forget when I did this because I did it over and over again in my preparatory stream. I did this many times. This is what I would have bet for. Any guesses? Well, because of the delay, I think I'll see your guesses as I'm doing it. But I'll show you. I mentioned earlier that I was not going to power this directly from the Arduino's 5-volt pin because it wasn't going to be able to put out enough power. And in fact, I did plan to, and then I didn't hook up my 5-volt power. So I had these two dangling wires here that should be connected to 5 volts, and then it will work a lot better. Let me hook up there, and there, turn on my power, wait for my power supply to come on. That's a very good sign. And now, using my test code, there we go. So not the code we were just looking at, but a little bit of test code I wrote earlier just to make sure that the servo motor worked. It's amazing. When you turn the power on, things work a lot better. Embarrassing. Let's load back up our knob code that we were working on earlier, and I can show it off to you. I honestly, I mean, I can believe that I did that, but I did it so many times today as I was preparing for this that it's pretty embarrassing. There we go. So now we have our motor spinning. Let's see. And S kind of spinning very strangely. Spinning very, there we go. So you can see, though, with the speed controller for some reason being flaky, and it could be a bad pot, as this thing is spinning, these LEDs here are flickering pretty rapidly. And those are the, the actual coils inside of the motor are turning on and off, on and off, on and off in a very specific sequence to cause this motor to move at the speed that it is. Make sense? Let's see. Why would it be not responding to speed control? Oh, it might be because, let's see. It might be because it's so, the step function, this is important to know, the step function here of the stepper motor, is moving a number of steps equal to the difference between the previous value and the current value. So if this was going to be 1,023 steps, and I told this motor that it takes 100 steps to move a full rotation and I want to move at 30 RPM, it might just be moving 1,000 steps really slowly. I think is what's happening. Yeah, in fact, if we come over here to the table, we can see it twitching back and forth here because now my potentiometer is turned all the way down, and so it's moving just a little bit with each rotation. But as I increase it, it's moving a little bit more with each rotation, which is not quite what we would intend it to do. Let me load up a slightly different piece of code that I think will make this a little bit more clear. This is the stepper button drive code, if you're playing along at home. A slightly more advanced way of controlling this circuit that I don't think I have a full circuit diagram up of, but it's essentially the circuit we've been working with a button on pin 7 and a button on pin 6, right? And the code is going to look very similar to the one we were just looking at, right? I'm going to include my stepper library. In this case, I chose to do a variable called steps per resolution instead of steps, but same idea. I also made it a const. Const means constant. It basically is another way of saying, hey, code, I'm not going to change this value anywhere while I'm running the code, so you can think of it just as a constant value. I tend to do that with anything that's going to be related to a physical constant, whether it's, where a button is hooked up or the parameters of my physical device, just because those things shouldn't be able to change while the code is running, right? So I have my steps per revolution function, I have my two buttons, on my case on pins 6 and 7, and I have my pins that my servo is hooked up to declared in an array. You'll remember back to last time we used arrays to hold a series of numbers in a specific order. So in this case, I thought it was a little bit easier for me to find and see and tweak if rather than using these pins in my my stepper definition down here, I broke them out into their own array. I'm also going to reuse those digital pins later in the code, but we'll see that in a second. So to take a look at this code, in my setup function here, I'm going to declare both of my buttons as input pull-ups, right? We talked about this a couple weeks ago as well, right? So those buttons can just be connected between the pin and ground. And if we declare them as an input pull-up, they will be read correctly. Set my speed to, I don't know, 60 RPM seems good. And then I'm going to set this variable last button time to 0, and we'll get into time a little bit later. But all this code says is, basically in this loop, if the button clockwise pin is low, if it's being pressed, step a single step, and in my case, a single step is 1 step in the clockwise direction, and then remember the time you press that button. Otherwise, if the counterclockwise button is pressed, step a step in the opposite of that direction, and remember that time. And then, just so things aren't locked in a current state, what I have down here is a bit of code that says if the current time minus the last time a button pressed was longer than a certain value, I think it's 1,000 milliseconds for me, I'm saying just digital write all those pins low. Just turn everything off. So after a second, if we haven't pressed a button, just turn everything off. Right? So we'll upload that code. What we should see is I should be able to press one of these 2 buttons and just have the motor move. Right? So I do that. There we go. Left, right, counterclockwise, clockwise, counterclockwise, clockwise. There we go. And you'll see when I stop pushing a button, there are always 2 of these LEDs lit. And it's sort of a random 2 each time. But those would be the last 2 bits of the last 2 connections to the coils that were energized, that happened to be energized when I let go of the button. Right? And then that timeout function, which is waiting a second after the last button press, just turns them off. So they're not just sitting there. There we go. You can, of course, step more than 1 step at a time. I find for something that's going to be super reactive like this, right? As soon as I let go of the button, I want this to stop. I would rather have it step a single step and then check if it should take another step and then check if it should take another step using some conditional logic. If that makes sense. Fun. If I change the RPM value, of course, if I come up here and say set speed, if I set speed to, I don't know, 15 RPM and re-upload, once it finishes uploading, we will see that things move a lot slower, which makes a lot of sense, right? That set speeds function is pretty handy, I will say. It prevents things from going faster than you intend them to. You can, of course, ask code to drive it faster than it will. And let's do this 120 RPM. I think that's faster than the stepper will handle. Let's find out. Actually, I didn't max this out earlier in planning, so we'll see what happens. Oh, well, there you go. Moves quite well. let's see. Let's do 240. Let's really juice this goose. We'll see what happens once it finishes uploading. Yeah. So right now the coils are transitioning too fast for the motor to actually move the required amount before the next coil turns on and the thing actually seizes up. So this will have sort of a maximum speed that it can rotate. This is also the 120 RPM was something it was able to rotate at when it had essentially no load placed on it. Right, there's no resistance other than a little piece of blue tape causing some air resistance on it. When you would start to impede the motion of it, say by putting a linear actuator on it or something like that, the maximum speed you'll be able to travel, of course, will be reduced. So that's the gist of stepper control, including set speed and step. Sort of the two key functions to use there. Questions? Nothing new in the chat. No questions there, which is easy enough. Can you make the buttons toggle continuous motor move? Oh yeah, so Brian asked a really good question earlier in the day, which was he was looking for a solution in which, so right now I'm pressing and holding, let me adjust my RPM so that this demo works again. Pressing and holding the button moves the stepper in one direction, and pressing and holding the other button moves it in the other direction. He was interested in a solution in which the buttons toggle continuous motion. And so yes, Brian, I'd be more than happy to. I actually worked up a little solution just before the stream. So what we're looking for is, I sort of invented some parameters for this project, but let's say pushing one button will cause it to rotate continuously counterclockwise, just tapping it, right? Pressing the other button will cause it to rotate continuously counterclockwise, and pressing both buttons together will cause it to stop. I don't know if it's exactly the situation you have, but I think it's a decent analog. kind of says have the stepper hold an arm to press the buttons for you. That's kind of circular in a way, isn't it? But let's take a look at the code for how we might sort of toggle the state of this servo. And this is something I wrote. This is also currently on the website, right? Link in the description. This is the stepper go stop example. And you'll notice it looks a lot like the example we were just looking at because it's based on the same code, right? I included my stepper library, steps per evolution. I have a button on pins 6 and 7. I said a single step is one step as far as I'm concerned. And I introduced this new variable called step value, which is going to start at 0. We'll see what that's used for in a sec. I'm also doing a timeout in this code, which we'll see later. And our 4 pins in my case are still 8, 9, 10, and 11. We're going to initialize our stepper to our steps per evolution value and pins 8, 9, 10, 11 in our case. And in our setup, let's see, do I need a serial value here? I don't think so. This is a holdover. We're gonna do the same thing we did in the setup code for the other program, right? I'm going to set my speed to, let's say 60 RPM in our case. I'm going to declare our buttons as input pull-up types, and the last time I pressed a button will be at 0 milliseconds, right? So here's the gravy in our loop. Let's start from the inside out. I'm going to say, the key thing here, let's just jump to the end and I'll show you what the point of all its conditional logic is this step. Every time I go through this loop, I'm going to say, stepper, please step a single step, which in our case is 1 step, times the value of step value, right? Now we said step value started at 0. So until we change anything, this stepper is going nowhere. Because if you say stepper step 0 steps, it will gladly step 0 steps and just do nothing. So what we're going to do is manipulate the value of this step value variable to make this stepper motor do different things. Inside this conditional logic, I'm going to skip to the second 2 steps here, right? If the clockwise button is pressed, the step value will equal 1. And if the clockwise button is not pressed, but the counterclockwise button is pressed, the step value will equal -1. So when we get to this final step down here, we will either be stepping 1 step forward or -1 step, which is to say a step in the opposite direction. I'm not sure if we said that out loud earlier, but for the step function, positive values are one direction of rotation, negative values are the other. And there's no way of saying concretely which is which. You could wire your stepper motor sort of reversed and your positive values would reverse direction, if that makes sense. So this is all going to be implementation dependent. But positive value is one way, negative value is the other, right? So this is how we implement, pressing button turns one way, pressing other button turns the other way. In fact, let me comment out some of this code, and we'll just do that. Let me comment out sort of these unnecessary things, right? So all this code is saying is if clockwise button is pressed, run one way, otherwise if the counterclockwise button is pressed, run the other way. Let's upload that, and I'll show you what it does, and then I'll show you why I had that other code. So coming over here, here's my clockwise and counterclockwise buttons down here. So so currently step value is 0, and so of course it's not moving, but when I press one button, that step value will go to 1. So now we're stepping in one direction. When I press the other button, step value becomes -1, and it's spinning the other direction. Now, we could do a number of things. We could have a third button that is a stop button that sets that step value to 0. But what I chose to do is sort of implement another thing where if you press both buttons, the stepper motor will stop. So let's look at how we implemented that, because it's kind of interesting. Here, I'm going to uncomment some, but not all of this code, and we'll look at that, and we'll add an else back into here. So I've added this new conditional statement here, which says if the clockwise button is pressed and the counterclockwise button is pressed, then step value goes back to being 0, right? So when we come down here to our step, we'll have 1 times 0, and we'll just stop moving. So let's upload that, and assuming I haven't typoed, we'll see what that does. It's not going to do quite, I think, what we want it to, but I'll show you, right? So step value starts at 0. I press one button, it starts rotating. I press the other button, rotates the other way. I press both buttons, it stops, but when I release, it starts rotating again. And it might start rotating in either direction. Now, you might be able to guess what's going on here, but it all has to do with limitations not of the Arduino, but of this guy. When I release these 2 buttons, yeah, Brian, I'm going to explain the millis bit in a second here, because it's what we're going to use to solve this problem, right? When I press these 2 buttons, right, if I hold these down for a second, I'll come back over to my code, right? the clockwise button is low because it's being pressed, and the counterclockwise button is low because it's being pressed. So my step value equals 0. But when I try to release these, I'm not going to release these both at the same exact instant. And so for just a moment, one button will be pressed and not the other. And so my step value will become 1 or 0 again. I'm just not good enough to release both these buttons at the exact same moment. So that's what I'm using this millis function for and the timeout for. So let's uncomment that and bring it back in. So what I've done is basically take all of that code, right? All of this, both buttons pressed or one button or the other pressed, and wrapped them in one more if statement. And that does this. If millis, right? And millis, we recall, is a function that returns the current elapsed time since the program started running in milliseconds. If the current time is beyond, greater than the last time a button was pressed plus this timeout value, and I set it to 500 milliseconds, half a second. If that is true, then you're allowed to run this code, right? If millis is not greater than the last time a button is press this timeout, we're going to skip all of this and just come down and keep doing steps, right? So what's going to happen here, for example, is if I press both of these buttons at once, for all the time that it is true, I'm going to update this last button press time, when I release them, I'm going to have about half of a second before I'm allowed to do a new action. Now, some of you who are thinking all the way through this might think that there's a little bit of a flaw here, and there is, but we'll get to that in a second. So if I upload that code and come back to the table, we'll see that now, as before, we will see our stepper motor start stopped. I press one button, it goes one way, other button goes the other way. I press both buttons, it stops. And when I release, I have that half-second grace period until things can start again. Now, the flaw in that code, of course, is that I'm timing that half a second not from the moment that the button was released, but basically every half a second from the point that that condition becomes true. So I don't always have a full half of a second. In fact, when I press both, so for example, let me start the spinning. When I press both buttons at once, because I'm not pressing them both at once, it actually takes half of a second for that change to be implemented, because I'm essentially pressing one button and then pressing the other. But because I pressed the first button, now I have to wait half a second for the other button to become depressed. So it's not a perfect system, and I want to leave it as an exercise to the reader to think about how you would modify this code such that you would get that half a second grace period from the moment that you release both those buttons. So thinking about ways that we can use timeouts or record the last time that we took an action using the millis function is a really useful way to prevent ourselves from having a situation where we have too many inputs coming in at once, and we don't want that to be, we don't want to possibly, take action that quickly. We looked at debouncing digital inputs last week or the week before. Very similar idea, right? We have things that are, in sequence very close together just because of the realities of the physical universe that we don't want to actually be possible in the real life. So we debounce them in a way by preventing them from happening too close in time. Does that sort of make sense? Worth playing around with for sure. Using millis will solve my problem. Yeah, there's lots of ways. There's lots of times, Brian, that using if you have things happening too closely in sequence, right? Especially if you're thinking about multiple things happening at once, whether that's things happening past each other or multiple button presses, using the millis function to record when they happened and sequencing your actions based on that, it can be a really useful strategy a lot of the time. I want to introduce one more concept tonight, and I see that we're just over 90 minutes, which is pretty good for us, actually. We only have one more little programming construct to get through before we finish off with some final questions and some looking forward to next week. And that is the do-while loop, or the while loop, W-H-I-L-E, the while loop. We looked at the for loop the other week, which is a way of stepping through an amount of code, a chunk of code, multiple times, a sort of a set number of times, right? We did it to I think we were to do something function that blinked an LED 5 times, and we knew going in we wanted it to happen 5 times, or we could provide the number of times that it was going to happen to a function, and then it would do a certain block of code a certain number of times. Travis says, your beer is empty, but I can tell you wish it wasn't. How do we remedy this? Well, I wish I had a second beer, but what I have is water. That I probably should drink more of. We should all drink more water. Just all the time. So where was I? While I think about having another beer, I'm going to do the following. I'm going to introduce a new do while loop. The do loop, or the while loop, is a way of iterating through a chunk of code multiple times without necessarily knowing ahead of time how many times you're going to do it. And let me just show you the code example, and I think that will start to make sense. PHN says, I would gladly donate a Jeff Glass Patreon beer fund. We're only like 3 weeks into this thing. I feel like the Patreon can't start until week 5. We'll do the forum first, then we'll do the Patreon. I think Squarespace is talking to me. We'll have a good old time. Do while works like this. Let's think about something for our code to do. Let's check my website and see, did I write an example code for this? Because if I did, we should just use that. Let's do electronics. Then check my own website in the middle of the stream. That's how classy I am. But I just want to make sure that I'm this whole like presenting the code ahead of time thing is new to me, and I want to make sure I do it right. Oh, so this will ultimately lead into the stepper homing example. But for an introduction, we'll just write some code on our own. So let's do the following. Let's define a variable called count, started at 0. And then in our loop function, I think I'm going to make sure I'm going to use the same hardware we already have just to make things easy. I'm going to define int button pin equals 6 because I have a button attached to pin 6 that'll make this easy. And then in my setup function, I'm going to do some in my setup function because I really only need this to run once to make my point. I'm going to delay for 500 milliseconds to get things started. I'm going to say serial.begin 9600 baud. We'll do this over the serial port just so you get the point. Wait half a second, make sure that serial is established, and then we will do the following. We will say while digital read button pin equals high, and curly brackets. And of course, to do a digital read, we'll need to do our pin mode function, our favorite pin mode function, button pin input pull up. And put a comment there for now. So what this while loop is doing is say, hey, you might be able to guess, run this chunk of code in between these curly brackets as long as this condition that I have put inside of my my parentheses here is true. We'll do it over and over and over again. And then when this becomes false, when this becomes not true, I'll stop. So in my while loop here, I'm going to say serial, let's see, I'm going to say count equals count plus 1, serial.println count, and delay, I don't know, 250 milliseconds is fine. So if I upload that, serial demo 3, we'll have to save that, upload that, come over here to the table. So actually there's nothing to see on the table here, so we don't really have to be here. We'll come back over here to our serial monitor, and we'll see that it just counts. Until I press the button associated to pin 6 over here. Button associated to button to pin 6? Pin 6. Something's gone awry. That's very strange. That's very strange. Let's see. Let's break this up a little bit. We'll call int button value equal, let's see, equals 1, and we'll break this up into 2 separate steps. Well, button value equals high, and we'll say inside of our loop, button value equals digital read button pin. Am I wrong about what pins that buttons are hooked up to? I swear I'm not. Well, let's find out. What am I missing? What did I unplug something? There we go. Whew, thank goodness. I thought I was losing my mind. So let me reset that code and we can run it one more time. Reset this over here. So now all this code is going to do is count upward from 1. And it's going to do it as long as we let it, right? It's going to just count and count and count until the integers roll over, and then it'll count again. But when I press the button associated to pin 6, it will stop and move on. And in fact, to show you that it's moving on, in the rest of my setup function, I'm going to say, I've moved on. And wrap that in a serial.println as well. This is all happening in the setup function here, right? Because I really only need this to run once to demonstrate the concept. But of course, you can do this in your loop function as well. So when we open our serial monitor, it'll count upward and upward and upward and upward. I press my button. It'll move on to the next part of the code. So that's the idea of a while loop, right? It's going to do something until some condition becomes false. And it's going to continue to check that condition every time it moves through the loop. I keep calling this a do while loop, and the reason for that is there's actually two slightly different flavors of this. And we'll do a practical example on the circuit in just a moment here, but I want to sort of show you the mechanics of this first. This is a while loop, right? So when I get here, it's going to, before it jumps into the loop the first time, check that this condition is true. And if it is, move into my loop. The slight variant is the do while loop, which looks very similar. It looks like this, which has this do keyword in front and the while comes after. And the slight difference between them is this code inside this do loop will always run once, because we're not checking that this condition is true until we get to the end. Whereas the while version may not ever run at all. In fact, if when I start up here, right, before I've ever jumped into my loop, if I say that this button value just is low, well, by the time I get to this while loop, button value is not high, so I'm going to skip the whole loop. So if I haven't screwed anything up, and I hope I haven't, when I run this code, open my serial monitor, I should just see I moved on. We didn't even get to counting to 1. We just skipped that entire loop. So when you're writing a do while loop or a while loop, it's worth thinking about, do I ever want there to be a case where this code doesn't run at all, or should it always run through at least once and then check whether its condition is true, right? So that's the difference between do and do while. Just checking the chat real quick. The demo did not work. Yeah, for sure. Can we watch it roll over to see what it does? Chris, it would take so long for it to roll over. Yeah, Brian, the do while function is a really useful one, right? It's in some ways, not to get too esoteric, but the loop function, right? This loop function that we know and love that runs repeatedly, is in a very real way, the code that runs the loop function is the equivalent of while true, do this thing. And because true is always true, this will happen for literally forever until you unplug power, which is what the loop function does, right? Now, often for the sake of our, usable code, it's more useful to have a sort of comparison in here that might someday return false, but saying while true is a perfectly valid function, right? So let's look at a practical example using a do while loop. And for those following along at home, this is going to be our motor do while function. Let's see here. So stepping through the code real quick, it's going to look a lot like the rest of our stepper motor code that we've looked at tonight. We include our stepper library, we define our number of steps per revolution, and then we create our stepper object using that value and the pins that the stepper is attached to. We're going to make use of a switch pin, which for me is going to be pin 4, because I'm going to add a new pin, switch to our setup that I'll show you in a second here. This analog input code I think is left over from something else. Yep, that is extraneous. We'll get rid of that. In our setup, I'm going to define our new switch as an input pull-up type, as we know so well. We'll use our stepper.setSpeed function to set it to 60 RPM. And then in our setup function, we're going to use a while loop that says while digital read switch pin equals high, take a step in the -1 direction. And what I'm going to set this up to do is use this as a homing routine for our stepper motor. Palmer asked a question earlier about do the servo motors home when you turn them on? And in a sense they do, right? Because a servo always, is going to a specific place. And so when you power the Arduino, they're going to just send that servo to a specific place. When you power up a stepper motor, right? If we think about this stepper motor here, this stepper motor doesn't know where it is. And in fact, the Arduino has no way of knowing where that stepper motor is in its total rotation. But we can use some external sensors to give the Arduino some sense of what our stepper is doing and where its position is in space when it starts up. And by doing this in the setup function of our Arduino code, we will always do it when we start up our Arduino. So it's going to take me just a little bit of time to set up this hardware, and then we'll play with this in person. So remove power, and I'm going to power off my power supply. Place your bets now as to whether that ever gets turned back on. And to our stepper motor here, I'm going to take my blue tape off and put back on this little wiggly wibbit that came with it. Oh, I guess this stepper cost $4.50 at American Science and Surplus. That's wacky. I have no idea what this stepper came to, or came from, but I just thought it was neat, and I bought it, and now you're the beneficiaries of that. Kenneth points out while I'm setting this up, the Arduino will have no way of knowing whether the motor misses a step. Yeah, Kenneth, we'll get to that in a second. We're yeah, we'll get to some mishaps and torturing some steppers in a second here. So by adding this bracket here, you can see I've sort of turned my rotational stepper into a linear stepper, right? As this, you can see if that's threaded there. As this screw rotates, and if I rotate it by hand, you'll see that this little platform moves in and out. And so by turning this stepper motor, I'm going to move this little platform sort of forward and back, as it were. In fact, let me demonstrate that. I'm just going to re-upload my favorite button drive code. Those of you who were here for our lens experiments 6 or 7 months ago, Chris, I think you were here for that. We were playing with lenses and LEDs. This is the code I wrote for that session. Oop, problem uploading to board. Well, those of you who bet that I would plug the Arduino back in win a prize. All right, so now that's uploading. Turn the power supply back on. Those who thought it wouldn't get turned on, no prize for you. All right, so now when I run my motor, you can see that little platform starts moving back and forth. So whatever this came from, right, because this is the this is the bracket that came with it, was used for some kind of linear motion. And I based on the shape of this thing, I have no idea what it was, but here we are. So for the sake of this demo, here's the last little bit of hardware I'm going to need, is that switch that I talked about earlier. But first, I'm going to take a little bit of my favorite construction material, sticky tack, and we'll just stick this motor to the table. All right, there we go. And now I'm going to take my switch. In this case, it's a push button, which has normally open and normally closed pins. And it's got a little sticky tack on it from my experiments earlier in the day. And I'm going to hook that up to ground. And I believe I said pin 4 was going to be my switch pin. There we go. And now I'm going to make use of this little protuberance on this platform to give my stepper motor a home position. Now, I'm probably going to have to keep my hands on this button because I think these things are going to run away from me a little bit here when I turn this thing on. It's also possible I got the direction wrong and it's all going to crash, but here we go. So let me upload my motor do while code. And just a reminder that when this thing boots up, it's going to set its speed to 60 RPM. And then as long as that switch remains not pressed, it's going to take a step in the -1 direction and then do some other stuff, right? So let's upload that code now, right? And once that code finishes uploading, we can see it's going to start to move. Now it doesn't know when it's going to stop, but when that button gets pressed, it stops. And then I asked it to move 10 rotations in the opposite direction. There we go. So now every time it boots up, it's going to find that home position using that switch. And if I move this switch, let's say a little bit further away, I will change the home position of, let's call it this motion platform here. Right? So we'll see that platform moving into place, moving. When it presses that button, boop, it stops and backs itself up 10 revolutions, because that's what I've asked it to do, right? Once I've exited this while loop, right, I had it set its speed to a little bit faster, delay for 2 seconds, and then do 10 revolutions in the opposite direction, right? So as you're thinking about building things with stepper motors, thinking about ways to cause them to home can be really helpful. For some applications, you may be able to guarantee that every time you turn your Arduino on, it will always be in the same orientation. Maybe it's because gravity resets your stepper motor driven cannon to its lowest position every time you remove power or what have you, excuse me. But thinking about ways to integrate sensors to give yourself a home position for your stepper motors can be really helpful. I used a physical button here, of course, because I have this, sort of made up construct of this platform with this little prong in front of it, and that seemed to make sense to me. But you could certainly use some other kind of sensor. You could use a beam break sensor, a little IR LED and a second IR receiver, and when something passes between them, that could stop your do while loop, and it could tell you where your home position was. If you're familiar with moving light technology, if you've worked in the theater or seen a rock and roll show with a bunch of big moving lights zooming around, almost all of those are based on stepper motor control, and so when you turn those fixtures on, they have to home. And they have to basically learn where their steppers are all pointed. And for some of those axes, right, you can just run your stepper motor into the end of its travel and have a physical hard stop. And let me show you what that looks like, right? Turn my button drive code back on just because that's a really easy bit of code to use. Let that upload, right? So my home position could be, in this example, I could just always move my stepper motor until it just can't move no more, and that's my home position. That's a perfectly valid way of solving this problem. You can have a hard stop. But using a physical switch, using a beam break sensor, using a magnet sensor or a Hall effect sensor is really common. For a lot of like color changing wheels in moving lights and technology, having a little tiny magnet on someplace on that wheel, having that wheel rotate until that magnet is in the line with the sensor, and now that stepper motor knows exactly where it is super common. So as you're integrating stepper motors into your devices, think about ways that you can give yourself the ability to home your motors before you use them. May not be necessary for your application, right? If using a stepper motor for you is more about the ability to have a defined speed of rotation, but you don't actually care about position, maybe you don't need a home position. I once worked on an art installation where we used a stepper motor because we wanted the rotating sort of pinwheel to have two different speeds. And we didn't really care what position it was in. We just wanted to say, hey, it's fast now, and when you pull this lever, it moves slower and does this other thing. Then that's fine. You don't necessarily need a home position, but if you do, using a while loop or a do while loop is a good way to find it. Speaking of, the reason that I used a while loop and not a do while loop in the setup for this specific code is I wanted to account for the case that what if my pin is already pressing my button when I turn the Arduino on? If that's the case, I don't want to take even one step. We are already there. If I had done this as a do while loop, which would look like that, then when I ran this code, I would always take one step, and then I would check to see if the pin is pressed. And if it already was, well, then we're already good. But that's not the functionality I want. I want to say if that button is already being held down when I turn the thing on, we are gravy. Make sense? Yeah. So that's the do while loop. I want to throw in a couple more things. Good time to throw in questions in the chat as well. Chris says 3D printers, CNC routers use steppers most of the time. Yeah, if you're thinking about a 3D printer, which has stepper motors to control each of the axes, when you start a print, typically it will home against little limit switches. It'll run each motor until it basically does what we did here. It'll press a button and say, I know where I am now, because I can always count the number of steps that I've taken since the last time I pressed that button and know pretty well where I am. And this goes back to a thing Kenneth said earlier, which is your Arduino has no way of knowing directly whether your stepper motor has missed steps. So in our button driving example here, I can drive my little platform back and forth by pressing this button. And if I've homed this in advance, right, and I was counting the number of steps I'd taken in each direction, I could know with some confidence where my platform was. But if I were to, impede the motion of it by squeezing it here, oh, it's making an awful noise. Can you hear that? Ooh. The Arduino is, if I wasn't coding it carefully, would still be counting steps that it thinks it has taken, and not. It would lose track of where the stepper actually is. If you've seen any 3D printed objects where your stepper has missed steps, or a CNC solution where your control device has no way of knowing, absolutely no direct feedback of where the stepper is. All it's done is home itself once, right? Say, I know where my 0 point is, and then counted steps back and forth from there to keep track of where it thinks it is. Systems that have active feedback that really do know where everything is are more complicated and honestly sort of beyond the technology range that a lot of like consumer 3D printers at least are making use of. I wonder if any of the more advanced 3D printers like the Stratus systems use any kind of positional feedback to make sure they are where they're actually supposed to be. I don't honestly know. What did I say? Oh, there's a couple more things about do while loops, and honestly about for loops that I want to show you. And that'll be the thing that we wrap up with tonight. And then we'll talk a little bit about what we're going to talk about next week. And then something to get your brains churning on while I'm showing you these last two things about loops are things that you might want to share, things that we might share on stream. I'm still thinking that sometime this week, and I don't know exactly when, or possibly the following week, want to have some way to start sharing projects with people on stream. This podcast that I accidentally got roped into watching all 4.5 hours of last night did a very successful Google Hangouts on stream, which I think was a really cool format. Lets people share off some of their project and some of their code and some of their things. So there's some good possibilities there. Anyway, while I'm describing some of these last loop things, shout out in the chat if you would be interested in sharing something, if you happen to be here tonight. I'd just be curious who out there might have something to share. Anyway, I'll talk at you while you're typing. The last two things about do while loops that I wanted to share with you are, and really about all loops, are the break keyword and the continue keyword. And they work like this. In fact, let's do them in a actual example. Let's see. Okay. Let's do them in our motor do while, our homing example that we were just working with. So remember, this is going to set the speed to 60. It's going to take steps in the -1 direction until it presses that button, and then it will know where it is, right? Let's say I want to have the ability to manually declare that a given current position is now the home position. Let's say this is in some kind of, I don't know, weird CNC environment where I want this this motor platform to either hit the end switch, or when I press this button on the face panel, that's home. So here's how I would possibly implement that. If I was doing a CNC machine, it might go a little more complicated than this, but here's the idea of the break statement. I could say, let's define what that button on our face panel might be. We'll say int button pin equals, we'll do pin 6 again because I still have that button set up. I could say if digital read button pin, which I don't think I capitalized. I didn't. Equals low break. And what break does is immediately exit a while or a for loop that you are inside of. It's basically saying, hey, this condition, I don't care. Just get out of the current loop that you're in. So in this case, when I press that button, it should break us out of that loop and do the same thing as if it had hit that homing switch at the end. So let's upload that and see if I've goofed anything up. So we'll upload our new code. We should see it home. Let's just let it home once. We'll make sure that, oops. Oh, it's acting like I pressed the button because I didn't set my pin mode. So we'll do pin mode, button pin, input, pull up. That will help things a great deal. So we'll let this run one more time. Let's just do this full home, and then we'll do our sort of manual home button that we'll do here. So we'll let this move all the way over here to our button. It presses that button, it should stop. Click, wait 2 seconds, and then back itself up 10 revolutions, right? So now, there we go. I'll just hit reset here. I hope I know which one of these is button on pin 6. I think I do. So we'll see it start to move again. When I press that button, it will immediately jump out of that for loop and then continue on to the rest of the code, stopping for 2 seconds, then backing up for 10 revolutions, just like before, which in this case is not particularly great behavior, but just to give you the sense of what the break function does. It jumps out of the loop. immediately upon hitting that break function. The other function I want to talk about is the continue function. I haven't really thought about how we're going to show this off here, but much like, let's see. Let's put this in advance. So the continue function basically says, hey, whatever loop I am inside of, skip the rest of this go through of the loop and start again. So I'll show it off like this. If digital read button pin, not capitalized, equals low, continue. Right, so what this will do is, I'm in my while loop, I'm going to be, heading toward that home button. But if this button on pin 6 is held down, I'm going to continue, which says, hey, wherever I am, just skip back to the start of this loop. I don't want to run any more code in here. We're done with this session of going through this loop. Go back to the beginning and start the loop again. So what the behavior in this case should be, unless I've screwed something up, which has happened already a couple times tonight, as long as this button is held, I'm going to jump into this loop. I'm going to see that the button is held down. I'm going to continue and just jump back to the beginning of the loop, right? So as long as I hold that button down, I'm going to essentially pause in the middle of my homing routine. I don't know why this is necessarily a function you would want to have in your 3D printer or CNC router, but maybe you do. So let's see here. So let it move forward. We can see our platform cruising along merrily there. And then when I hold that button, it's going to pause. Now I'm not exiting out of that loop. I'm actually still in the middle of that loop. I just have this if statement ahead of time that's saying, hey, if that button's held down, wait on what you're doing. Go back to the beginning of the loop and do nothing else. And you can see when I release that button, things pick up from where they were. Right, so just to be clear, I'm not actually pausing the loop, I'm jumping back to the beginning. In this case, that bypasses the code that was making the stepper run, and that's what's creating this pausing behavior. And now you'll see when the loop completes and it presses the button, click, waits 2 seconds, and backs up 10 revolutions, same as before. So that's the continue function, right? It lets you say, hey, based on this set of circumstances, I don't actually want to do the rest of this time through the loop, but I might want to continue doing future iterations through the loop. You can use break and continue also with for loops, and I'll show you that right now too. I see lots of things happening in the chat. I'll be over there in a sec. Let's keep spinning those good wheels. Let's do a new example. We'll use the serial terminal just because it'll be an easy example to write. How to use break and continue inside a for loop. So we'll start up our serial port here with serial.begin, and then I will say, we'll just do this all in the setup function, so we'll only run it once. I'll say for int I equals 0. I is less than 1,000. We won't ever let it get that high. I plus plus. And my basic operation will be serial.println I, and delay, I don't know, a quarter of a second. Again, seems like a pretty decent pace. So let's upload that. Oh my goodness, always have to save. Thing. I'm gonna hate myself later when I have a bunch of these scratch files lying about with assorted names, but here we are. So let that upload, and you can watch it stimulating behavior while I there we go. So we get that idea, right? It's just counting by 1 every quarter of a second. And I'm going to move this delay up here for a pretty good reason, right? So same idea, wait a quarter of a second, then print the number. What I will insert in the middle of these two is say, if I mod, remember our modulo operator from a couple weeks ago? If I mod 10 equals 0, continue. So before I run this, think for a second about what you think is going to happen when I run this code. Let's upload that, and we'll see if you're right. Uploading, and I'll open my serial monitor. And you'll see, yes, I hope that's what you predicted would happen. So what this code is doing is it's still counting up by 1. We're still going through this loop, number by number by number, but when the number is divisible by 10, in other words, when its remainder by 10 is 0, I hit this continue function, and when I continue, I skip over the rest of the code in my loop and start back from the beginning. So what we're seeing here is basically skipping every multiple of 10. It's not getting printed, but you'll see there's an additional little pause there because this delay function is still happening, right? Every time through the loop, I definitely hit delay. I only print if it's not divisible by 10. That sort of makes sense? I could do the same thing with break, except this will just, let's start at 1. This will basically stop my loop when I get to the number 10, because 10 is divisible by 10, and when that happens, I'll jump out of the loop. And here, I'll demonstrate that. We'll write another print command. We'll say, I'm out of the loop. We'll upload that. And we'll open our serial monitor. When I do, here, let's clear that. When I get to 10, I don't actually print 10, right? When I got here, this was 10. I delayed for a quarter of a second. When it was divisible by 10, I broke out of my loop and I said, I'm out of the loop, right? So that's continue and break. I would caution you in terms of code style, especially thinking about break. Break feels like a really useful function, right? I'm running through this routine. I'm doing things. I want to add more ways for myself to sort of be done with this loop, right? I would, caution you to think about, is there a way of incorporating whatever you would have said in your break statement into the condition of your while loop or your for loop? Only because, right, this while loop, right, for us has 2 or 3 steps in it, but might contain in a longer set of code, 200 or 300 lines of code. And if you're sprinkling break commands all throughout your loops, it can sometimes be hard to determine why it was exactly that you stopped iterating through your loop and jumped to the next thing. So rather than relying on break, although it's a very useful command, think about if there's a way to modify your conditional that's going to stop your loop to begin with, to have that break statement built into it, or if you really need that break. Just something to think about. Having said all that, let's check back in with what's happening in the chat. I see lots of good projects coming in. Interested in other projects? Chris can share the crazy Switch Oh yeah, I saw a picture of Chris's Switch project. That would be super cool. Controlling some house lights, I think in a church using servos. Palmer's still diving into things. Ken says, wow, a while true loop with breaks buried in the middle of the code is common. Yeah, for sure. So if your while loop is happening forever, while true, then having a break somewhere is the only way you're ever going to get out of it. If I was reading through a piece of code and I saw while true, then I would know to look for a break statement somewhere, because otherwise we're stuck here forever. If I saw while something, I might not go hunting for that break statement. It'd be a little bit harder to parse. Palmer's got a ClearCom call light project that he's working on, which is very cool. Call signal is 30 volts on this call light project. Yeah, so this might be a good segue into what I think we're going to talk about next week, which is a couple of things. We're going to talk about ways of interfacing the Arduino with higher voltages or higher currents, right? We said that our high and low on our, at least on our Arduinos, are 0 volts or 5 volts, or for sometimes 0 and 3.3 volts, for most of them 5 volts. We're going to look at ways of interfacing higher voltages safely into our Arduino, but more specifically, we're also going to look at outputting higher voltages or higher currents, right? You remember that most of our Arduinos have a 20 milliamp current limit on all of our output pins? Well, that's decent for driving sensors or servos or basic actuators, right, which are really drawing very, very little current. But what if you wanted to drive one of those DC motors we were talking about earlier, or maybe a relay that might need a larger amount of current to drive it and yet could drive a higher amount of current. So we're going to look at using the Arduino to drive transistors and FETs and relays to control higher current or higher power devices. That'll be a good discussion, and that is probably a whole college level course we could just do on that. Well, one that I've never taken, but we'll at least get into how you can control higher current or higher voltage things using the Arduino pins. And the other thing I'm thinking about, so it might be next week or maybe the week after, is doing just a little bit of a back to basics on wiring components. I had somebody say to me the other day, the thing that I'm having a challenge with is, I'm wiring all these circuits, and you say, put a resistor in line with this LED, just use any resistor. But I don't know what resistor I should be using, or frankly, even why I'm using a resistor. So next week, depending on how the lesson plan shapes up, either next week or the week after, I want to come back to this idea of taking a closer look at the components we're using, the LEDs and resistors and capacitors, and how the actual sort of fundamentals of electricity are working in our circuits. That for me is a pretty natural sort of follow-on from using transistors and things to drive higher currents. So it might happen next week, or if we have enough to talk about with transistors and FETs, it might be the week after that. But that's sort of where my head goes, if that makes sense. Chris says, do we get to see Jeff let the magic smoke out of an Arduino? You will probably see it someday just on accident. It's not, in fact, I'm trying to think if I have one that's pre-blown up around here anywhere. I don't think so. I usually throw them away because they stink pretty badly. But the next time that I have one that's totally dead, I will make sure to save it, and we can all look at it together. Interested in the electronic stream? Yeah, I think it would be helpful. Part of the genesis of this was thinking about people who had an Arduino kit, gathering dust in their closet, hadn't had it out in ever or a while, and were sort of working their way through learning about it, which is awesome. And I realized that we've been focusing on these these black boxes of systems. Plug this thing in and it works and it does this, and not going super deep into how anything works. And once we learn a little bit about powering higher power devices, I think we'll have enough interesting things under our tool belt that going back to basics would be really valuable. Yeah, that seemed like a thing. I think we could certainly do that. Oh, not as good as beer, but we should all drink more water. I think that's all I've got for tonight. I've certainly made it through the lesson plan. We came in at just under 90 minutes at 2 hours and 9 minutes to date, which is pretty good for us. Yeah, I think that's where we'll probably call it for tonight. Thanks again for joining us on a chill Sunday night. Palmer says, if your YouTube video was titled "What to Do with Your Arduino Starter Kit," would it get a ton of views? Yeah, it's true. It's true. I hadn't really thought about it that way. Kenneth actually sort of grokked that that's what this series was about, and put it into words in a way that I hadn't just a couple days ago. So my one thought I've had, which is, and I think this is a crazy idea, but if I do it, I want you all there for it, is buy a brand new Arduino starter kit and do 1 mega stream that sort of covers some of the same ground that we've covered, and just doesn't stop until we've touched every part of that starter kit and shown how it works. That is probably too ambitious. It's probably a little bit nuts. But I think it would be, I think it might be a fun time, and maybe valuable for people, or maybe not, maybe just kind of a crazy thing to do. Given the depth that we've gone into so far, we're probably talking about a 12-hour experience, which is you can see the headlines now, this Arduino streamer spent 12 hours unpacking a whole Arduino kit. You can too, which feels just not, it feels a little cheesy. But I don't know, maybe someday, maybe once we've gotten through a few more episodes of this, maybe we'll dive into that. That's a good question for me to close things out with while I say my goodbyes and throw it into the chat. What pieces of your Arduino kits have we not talked about yet that you're really interested to try, right? Knowing that next week we're going to talk about transistors and high-powered things, and either next week or the week after we're going to talk about resistors and capacitors. What else do people have in their kits out there? I certainly, I haven't actually bought one of those kits in ages. I think the closest thing that I have is, forgive me for the overhead shot, is this guy, which was given to me by my father-in-law, which is from Elegoo. It's a 37 sensors kit. It's really been a lot of fun. Has all these various, inputs and outputs and sensors. It's got a heartbeat sensor and a tilt switch sensor and a metal touch sensor, which I'm not entirely sure what it is. So we can have some good fun there. But I'm curious what people have in their kits that they've been pulling out of their closets. Michael Trudeau says the number pad and the number LED readout pieces. Ah, yeah, that would be cool. Those 1, 2, 3, 4, 5, 6, 7, 8, 9 0 pads and the 7-segment displays. We could do a good thing on 7-segment displays. Chris says the nuclear reactor. Not sure how to use it for my kit. That might be. We might have to make that a private stream. I might have to make limit the FBI account from seeing that stream. Michael Glass 7-segment display. Yeah, 7-segment display would be really good. We've actually there's depending on I'll be in touch with you, Michaels, to see which 7-segment displays you have, because there's a couple different ways of driving them. Tao says, we made the LED blink, so most of the parts. Brian says IR sensors. Yeah, there's a lot of good ground to cover. I feel like 7-segment displays, displaying numbers and getting displays into here will have to be a part of this at some point. And then IR control, I think, would be really fun. And then other input methods. We'll just keep going. Yeah, thanks, y'all. That's really helpful. That's really super, super helpful. And we'll see how we can integrate those into future weeks. In the meantime, I think let's call it there for tonight. Thank you again, everyone, for hanging out with us on a Sunday night. And for those of you who missed last week, I know some of you had virtual parties and things to go to. I hope you had a good chance to catch up on last week's stream. One thing that to be honest, I tried to do was to recut the streams into sort of bite-sized, like actual YouTube videos. But the amount of time that I'm already putting into making this stream possible, the additional amount of work to re-edit a stream into a YouTube video, got to be admitted. I'm just not good enough yet. I'm just not. I don't have the editing speed to make that happen. So that's a future dream of mine. Is to release more videos that have actual sort of digestible content in a less than 2 hour and 13-minute form factor. Michael says we can post photos in the next event of whatever we have. Yeah, I'll put some information when I put out the next Facebook event. I've been trying to get those up by Wednesday or Thursday of the coming week. Yeah, we'll figure out some way for people to share things and get some people on here to talk about their things that they share, because I think that would be I think that'd be fun. I just want to know what you're building out there. I think it's a really good time. Yeah. Thanks, y'all. Thanks for a good Sunday. I hope you're doing okay out there. It's a weird world right now, but it's nice to sort of cocoon in here, at least for me, for a couple of hours each week with y'all, and just build things and make things. And as we go forward, I'm excited more and more. There's going to be more and more things that you guys ask that I don't know, and I'm really excited for that. For us to go down some rabbit holes together and learn some things together. So yeah, have a wonderful week. Have a really great time out there. I'm gonna go get another beer because I think we've all earned it. You've been great. Keep making things. Stay safe. If you blow up an Arduino, I want to see a picture of it. Thanks, y'all.